Hello and welcome to today's video in mathematics. Today we are going to investigate the question of when a vector field is a gradient field. More precisely, we're going to see a necessary and also a sufficient set of conditions that will guarantee that a given vector field is a gradient field. So the question we'll be talking about today: when is a vector field V defined on some domain D, subset of R to the n, when is that a gradient field? Of course, one possibility is to just see if we can find a potential for that gradient field, and then we have a proof. But it would be nice to have easier conditions for that. So let's see what we can find in that respect. Let's say we have a gradient field, then there is also a potential for that gradient field. So let F be a potential. That means F maps from D to R. And let's also assume that the gradient field V is differentiable, because then we can say something about the higher order derivatives of the potential F. So for a differentiable vector field, V, if V is differentiable and V is the derivative of F, then that means F is differentiable twice. And let's also assume it's continuously differentiable. F is therefore in C2. And that means by Schwarz theorem, we get that the mixed partial derivatives of second order of F are equal. So what we have is d2f dxi dxj is equal to d2f dxj dxi for all I that are not equal to j. What does that mean for V? Well, the second partial derivatives for F are the first order partial derivatives of V, of the Vj's in particular. So what that means is dVj dxi of x is equal to dVi dxj of x for all I not equal to j. So here's a condition that is necessary for V to be a gradient field. However, the condition is not sufficient. It will be under an additional set of assumptions, and we'll talk about that in a minute. But let's just make a quick note about this necessary condition here. So that's our first theorem for today. Let V d to Rn be a continuously differentiable vector field. And then we can say if V is a gradient field, then the following must be true. The partial derivatives d Vj dxi of x and the partial derivatives dvi dxj, so we're changing the order, so to say, those are equivalent for all I, j in 1 to n with I not equal to j. So we take any two components, vi, vj, and we differentiate those. We differentiate vi with respect to xj and vj with respect to xi, and that must be the same result for all possible pairs that we can consider here. Okay, if that is not the case, then we know that we cannot be a gradient field. However, note that if this is the case, that does not mean that V is a gradient field necessarily. As I said, there's one more condition that we need to ensure that this is also a sufficient condition. And that condition relates to the domain D. So there are domains that are nice in a certain way. And for nice domains, this is also a sufficient condition. But there are domains where this does not hold. More specifically, domains are nice if they have no holes, basically. That's what we're going to define right now, right? So domain with a hole is something that we don't want here. That can destroy the sufficiency of that condition. If the domain does not have a hole and is connected, then this condition will also be sufficient. And the term for domains like this is so-called simply connected domains. We'll define that right now. So here's the definition of simply connected. We start with a connected set, so let D be a subset of R to the n, be a connected set. Then, if we consider any closed curve in that set D, then we can take that curve and contract it, make it smaller and smaller and smaller, until it collapses to a single point. And the precise definition is, if that contraction can be carried out in a continuous way to arrive at a single point that is still contained in D, then D is simply connected. Okay? So if D has a hole, then we can consider a curve around that hole, and of course we cannot contract the curve to kind of swallow that hole, right? It will be stopped by the borders of the hole. So that means if D contains a hole, then this contraction cannot possibly succeed. And that's the cases that we want to exclude. Okay, so we start with a connected set, and the definition is if every closed curve in D can be continuously contracted to a single point in D, then D is called simply connected. One particularly important example of simply connected sets is convex sets. Convex sets cannot have a hole, because if there was a hole in the set, then you could choose 2 points on either side of the hole, and you could arrange them in a way that the line connecting those 2 points would pass through the hole. And for convex sets, remember, every line connecting any 2 points in the set must be contained completely in the set. So if it passes through a hole, then it's not contained in the set anymore. Right? And that's the problem here. So every connected set is also, every convex set is also simply connected. Every convex set is also simply connected. And in practice, that's one of the most important examples of simply connected sets. You will notice that this definition is not really precise in the way that you're used to, mainly because we did not specify what we mean by continuously contracted to a single point. So what exactly is a contraction of a curve? When is it continuous? And what does it mean for a contraction to be a single point? Of course, you can make this more precise. It's quite technical to do that, unfortunately. So I'm not going to spend a lot of time on that. Instead, I'm just going to show you some examples, and it's probably enough to bear in mind that first thing, convex sets will always work. And second, basically what that means is if the set contains a hole, and even if it's just a single point that is punched out of the set, then it's not simply connected anymore. Sets without holes are simply connected. Okay, but I could not write that down as a definition either, because I would have to specify what I mean by a hole. And that's a whole lot more complicated than contracting curves, if you want to do it precisely. Okay, so here's a couple examples. This here, that's a convex set. So that is obviously also simply connected. So that is convex and also simply connected. Now here's an example for a set that is not convex, but still simply connected. Again, it doesn't have a hole. Any closed curve in that set can be contracted to a single point. Now let's see some counterexamples. The most prominent counterexample is probably a donut. So this set here, where we exclude the hole. So here's a hole in there. And that means this set is not simply connected. And another example of a not simply connected set, let's take again a circle or disk. And let's punch out just one single point. So we'll take the whole disk, but we'll punch out the middle. So there is a hole again. It's just a single point, but that's enough. So any contraction, any curve around that point can be contracted, but the single point that it would have to contract to is exactly the missing point, and that is something that cannot happen. The single point must also be contained in D. Okay, so this is again not simply connected. Okay, one example of a curve that cannot be contracted. Let's see that as well. If you go into the donut example, for example, here's a curve around the hole that cannot be contracted to a single point. And of course, other curves in that example can be contracted to single points. The point is there are curves that cannot be contracted, and for a set to be simply connected, every curve, every closed curve must be contractible to a single point. And that's the problem with these sets here. Okay, so that condition, simple connectedness of the domain, that is enough to make our so-called integrability condition that we've seen before, to make that sufficient as well. So let's write down this result as today's second theorem. So let D be a subset of R to the n, be open and simply connected, let V be a vector field on D, and let that be continuously differentiable. So that is a continuously differentiable vector field. Then V is a gradient field if and only if the following condition holds. That condition is again dvi over dxj of x is equal to dvj dxi of x for all ij from 1 to n, with I not equal to j. And this condition is often referred to as the integrability condition. So basically it tells us whether a vector field has a potential, and in a way that means whether a vector field can be integrated. Okay, so with a simply connected domain, this condition is the one you want to check. Of course, also with a non-simply connected domain, it is enough to exclude non-gradient fields. So if that is not fulfilled, then the field cannot be a gradient field, no matter what the domain is. But if the condition is fulfilled, the domain needs to be simply connected, so that you can also say, well, we have this condition, we have simple connectedness, so the vector field must be a gradient field. So that tells you there is a potential. It does not give you the potential, so you will still have to resort to integration to find an actual potential of that vector field, but at least it guarantees you the existence of a potential. And sometimes that is all you need. For example, if you integrate along a closed curve, and you know the vector field is a gradient field, then you can immediately be sure that the result is 0. So you don't even have to know the potential, you just have to be sure there is one. Okay, so this concludes our discussion of gradient fields, and we'll see a little more about vector fields in the upcoming videos. I'll see you then.